we want to specialize Euler's equations for a case of a steady precession of a gyroscope. So, of course, the first question is where to put the what coordinate system to use. We want to put the center of the coordinate system at the fixed point of motion. Okay? As it happens in this picture, it is also in the center of the gyroscope and in the center of mass, right? But it does not have to be. The important thing is that it must be at the fixed point of motion. Okay? And then, of course, we must have our matrix of inertia constant, right, in our chosen coordinate system. So how would we choose the coordinate system so that it has the center at the fixed point of motion, it is convenient, and the matrix of inertia of a gyro remains constant in that system? So, tell me. Well, by say elimination, well, it can't be the inertial system fixed to the ground, right? Because the gyro will move in it, and therefore the inertia would become variable in such system, so it's a disaster. So we want the system that there are essentially two possibilities. One, we just fix the system on the body, right? So the system fixed on the gyro and moving with the gyro, right? Well, this is doable, but the better choice is to put the coordinate system in such a way that it precesses with the gyro but doesn't spin. Okay? So even though then it is not completely fixed on the gyro, the inertia matrix remains constant because of the symmetry of the gyro, right? So this is how we set up the system. X, Y, Z, okay? And this system precesses around vertical axis with angular velocity capital omega, as the gyro does, but the system is not spinning with the gyro because we don't need it because of the symmetry of the body. Okay? So now here you have an example of a coordinate system in which the inertia matrix is constant, but it is not completely fixed on the body. And that's why in our green equation here, I make an explicit difference between the angular velocity of the coordinate system and angular velocity of a body. Okay? So, if we have chosen our coordinate system, now we need to compute all these things in this equation. Okay? So we need to specify what this is, and what this is in the coordinate system as shown here, and then do the cross product, and we'll have our solution. Right? So I am displaying this for the record. Choose coordinate system that precesses with the gyro but does not spin. Okay? And I am displaying this one for the record too. So this is, we already know. In that system, the inertia matrix will be constant. Due to symmetry, of course, this is the case. So off-diagonal components are equal to 0. And also, maybe we should remember that because of rotational symmetry, Ixx equals to Iyy. Okay? And now what's left is to evaluate this. So now the precession is steady, right? Steady means there is no accelerations and stuff, which means there is no change in angular momentum if axis of the coordinate system would not rotate, right? So this first bit is 0, obviously. So we are only interested in this bit. And we remember that this is the meaning of the capital omega, angular velocity of the coordinate system. So what are the components of that angular velocity in our system XYZ? Okay? This is the angular velocity of the coordinate system, capital omega. And what are the components of capital omega in XYZ coordinate system? Oh, come on. This you have to tell me. Well, Z component is omega cosine theta, right? X component is minus omega sine theta, right? And Y component is nothing. Okay, so this is now our angular velocity of the coordinate system, minus omega sine theta I, nothing in J, and omega cosine theta in K direction. Okay? Now, omega is the angular velocity of our gyro, lowercase omega. So what are the components of lowercase omega? What's the lowercase omega? The angular velocity of the gyro. Well, the idea 0, 0, phi dot, not good, because this is not the total angular velocity of our gyro, because it also precesses, right? It's spin plus precession. So now, girls and boys, remember that angular velocity is a vector, the same as linear velocity, which means you just add angular velocity as vectors the same as you add linear velocities of vectors, which means that the angular velocity of our gyro is angular velocity due to spin plus angular velocity due to precession, just added as vectors. Okay? Which is something like this. Okay? So in x direction we have minus omega sine theta. In y direction we have nothing. And in z direction we have phi dot, which is due to spin, plus omega cosine theta. Right? Piece of cake. So now we have our both omegas, and we can actually write immediately the equation for our angular momentum, okay? Which is, because the matrix is diagonal, it's just Ixx times the angular velocity in x, 0, and then Izz times the angular velocity in z direction. Piece of cake. Okay? So then, as we noted before, because precession is steady, this is 0, and we need to evaluate this. I think in primary school, people suggested that it's possible to compute vector products as determinant of matrix 3 by 3 set up this way. So I don't know. I use Mathematica for such things. But in the absence of Mathematica at the exam, maybe it's good to make sure, to be sure that you can take vector products at the exam. Okay, so now, if we look at this result, so we can, and then look at how H and how capital omega look, we can easily see that most of the stuff here is actually 0, right? Because if we look at I direction, here we have omega y, but omega y is 0, and here we have hy, but hy is 0. So this goes away. So there is nothing in x direction. If we look at z, we have hy here, but hy is 0, and omega y here, but omega y is 0. So this goes away. So the only thing that is left to worry about is the y component, okay? Or the thing along J. Okay? So if you actually do it, sometimes I ask people at the lecture to actually do the algebra, but luckily for you, not today, right? So if you actually substitute the values, so as we said, nothing in x direction, nothing in z direction, and this is what we get in y direction. Okay? Now, I'll repeat here that the meaning of the green equations as compared to the meaning of the Newton's second law is that this is the motion, the left-hand side is the motion and the mass distribution, and the right-hand side are real forces, which means that to maintain or produce steady precession of a gyroscope, as in this picture, you need a real moment acting along y direction. Okay? Somebody or something must be sitting there and acting with this moment on the gyro. This is the moment acting on the gyro. Okay? So the red stuff is this line for y direction rewritten slightly. So you take omega phi dot sine theta out of the bracket, and then you get this stuff inside the bracket. Okay, so again, very quickly, capital omega is the angular velocity of precession, normally low. Phi dot is the angular velocity of spin, normally high. Theta is that angle between axis of precession and axis of spin. And then IZZ and IXX are entries in the inertia matrix. Now, normally, IZZ is larger than IXX, and therefore, normally, tau y is positive. Okay? So, if we look at this picture, again, we get a positive torque acting about y, along y direction. Okay? So, if we use a right-hand side rule, well, my hand is too big for this, right? So we are acting along y we are trying to increase angle theta, right? So the moment that acts like as if tried to increase angle theta fails to increase angle theta, unfortunately, but produces the precession around the axis, vertical axis. Okay? This is actually what we saw. Well, what we actually didn't see, but we considered that spinning wheel on the string, right? The gravity was acting as if trying to increase that angle theta, but it wasn't dropping, it was precessing, right? So this is what we are seeing here now. Anyone who has trouble, as myself, with visualizing stuff does not need to visualize anything anymore, because we have algebra in support of it, and then it's the red equation, it is what it's saying, right? Even if you don't believe all these pictures, you will have to believe the equation. Okay? So this is the equation which we will later use to solve our case study. Okay? For the gyroscopic grinding mill. But now we will consider what's happening for the gyro. Okay? So the first thing which happens for the gyro is that the angular velocity of spin will be in the thousands of RPMs, and the angular velocity of precession will be very small, which means this red bit is becoming very close to zero. Omega divided by phi dot is becoming zero, essentially, and therefore this thing goes away, and we are getting just this. Okay? And then the second thing we note, for many practical cases, the angle theta is 90 degrees, as was in the case I showed, right? The angle between the axis of precession and the axis of spin is 90 degrees, right? So sine of theta is 1, okay? And this is the magical equation. Angular velocity of precession proportional to the torque acting along y direction. And this is the proportionality constant which we know, because we know the velocity of spin and we know the inertia around z. Okay? Now, I'm surprised that nobody is fainting now, because I'm saying that the moment is not proportional to any acceleration, but to the velocity. And actually in a completely different direction, right?